All right, ladies and gentlemen. So thank you very much for coming. What you're seeing behind you is because some of the demonstrations I'm going to do need to be done on a small scale for safety considerations. I have a video camera that you can visualize it. The other thing that this is doing is that this is actually recording this presentation. Now, we're not dealing with like HBO or whatever quality stuff, but if you're interested in showing this to some of your friends, to the kids, or to anyone, neighbors, whatever the case is, grandma, grandpa, the like, I will get your email address at the end, and then I can send you a link to this such that you can go and watch this at any time during your, any time that you want. Anyway, my name is Dr. Roy Jensen. I teach chemistry here at the university. Now, many people here, how many people here in like grades like 1 to 6? Okay. Anyone over in grades 7 to 9? 7 to 12? A few? Okay. So some of the stuff that I'm going to talk about is stuff that you haven't seen yet. You've seen all the displays outside. Those are really cool. Actually, some of my demos are up there right now, so I'm not going to repeat my demos in here, which leaves me to do the more dangerous ones. I hope that's okay with you. Okay. I do want to start off, though, talking about molecules, because what a chemist does is he looks at atoms and molecules in the way of trying to identify them, trying to make new compounds, or if you're interested in forensics and the like, you're looking at analyzing compounds or analyzing samples to try to figure out what they are. These are molecules formed from atoms. So every little dot there is an atom. I can do it this way. That'll work. So every little dot is an atom. The black one we typically label as carbon. The white one is hydrogen. The red one is oxygen. And there isn't any blue ones in this one, but if I pull up a different molecule, you'll note that it has black, white, red, and blue. Those are nitrogen atoms as well. So carbon, hydrogen, oxygen, and nitrogen. And depending on how we arrange these things, we get different molecules. So to the kids in the audience, there it is. Here's a nice simple molecule right here. Okay. This is a compound this is a drug. This is a drug that your parents have given you. Yes, your parents are starting you on the road to drugs. Okay. Oh yeah. What drugs might your parents have given you? Yes. Vitamin D is a drug. This doesn't happen to be vitamin D, but you're right, it is. Gentleman behind. Yep. Vitamin C. What else? Tylenol. Okay, Tylenol. This is the molecule for Tylenol, acetaminophen. Okay, carbon, hydrogen, nitrogen, oxygen. I'm going to toss it to you and realize that my aim is pretty bad, so I apologize in advance if I clock like the student of mine in front row. Oh well, they're the person behind. Not a big deal. You can't keep it. I need those back, okay? But you're allowed to look through them and pass them around. So your parents take drugs too, most likely. Like this one right here. They take it in the morning when they wake up. What might that be? Caffeine, yeah, in coffee. So this is caffeine. Your first taste of caffeine, I hope. Or maybe not. Like I said, my aim is pretty bad. So caffeine, take a look at it, pass it around. And there's a couple more here. Those two are drugs. They're legal drugs, and they're administered, as appropriate. These ones, the last two that I've got, are not quite legal. This one right here is the active ingredient in marijuana. Okay, so there is some degree of legality with it. And to my former student, or my current student still, I think it is, right? Yeah, still. Shows up to class once in a while. Here we've got for you, madame, 170 grams of cocaine. I'm just going to pass these around. You can feel them, look at them. Basically, that's atoms. That's how they're bonded together to form different molecules. Okay. How many people here have been to the ocean? Okay, good. All this is water. I'm just adding water to this container. Okay. So when we breathe in oxygen. Does anyone happen to know what we breathe? Yep. We breathe out some amount of carbon dioxide. Now, carbon dioxide is a gas that exists in the air around us, but it is also absorbed by water. And so you don't see with carbon, there's carbon dioxide up there, so if you want a little bit more of carbon dioxide, it's right here. What I'm going to do with it, though, is if we cool it down and cool it and cool it and cool it, we can actually make solid carbon dioxide. So I'm going to take some of this carbon dioxide, put it in a glove. There we go. Carbon dioxide is also known as what? Does anyone happen to know? Come on down. You can sit at the front. Yes, sir. Why is it called dry ice? Okay, it's dry ice. That is the correct terminology. Dry ice doesn't actually go through a liquid phase. Water, ice, when it melts, gives you a puddle of water. Dry ice, when it doesn't melt, it doesn't produce a liquid, it goes straight to a gas. And you can see that inside of this glove. And I'm just going to do that one more time. It's actually really cold, so handling it with your hands is something that should be done by professionals, so don't want to keep it in contact with your skin. But you can feel how cold it is in the fingers of these gloves as they pass around, and they're just going to slowly, slowly, slowly inflate these gloves. Pass it around. I'm going to add some dry ice to water, and you're going to see the bubbles, because the bubbles are going to be captured in the water. Now there's something else going on in here that you can't see. When dry ice is in water, or when carbon dioxide is in contact with water, like on the oceans, the rivers, the lakes, it actually absorbs the CO2 and forms an acidic solution. So what I'm going to add is a little bit of an acid-base indicator. And you can see that it is distinctly yellow. And I'm just going to add a base, and we're going to see that it will really make the solution go back to being acidic. So this is a special type of indicator. You've probably worked with beet juice, cabbage juice in your labs. There's pH paper in the senior classes. This is another type of indicator that is going to go through the rainbow of colors as it goes from being basic to acidic. And we'll just watch it for a few seconds. Now it's going through a green phase. Slowly, slowly. And we'll just let it go right there. And as it proceeds, it's turning yellow. So we have this indicator that's going through the rainbow of colors. It doesn't go completely red. There we go. There's the yellow phase of the indicator. But one thing I want to talk about in terms of chemistry is safety. So you see I'm wearing safety equipment. What other safety equipment do you see scientists commonly having? Goggles. So safety glasses I have available for when I need them. At the back, in the blue, yeah. Gloves. I've already used a couple of gloves as well. So lab coats, safety glasses, gloves, common things that we have for safety equipment. In addition, we have safety equipment available to us. Okay, we've got fire extinguishers in our labs. We've got emergency showers in case we get covered in chemicals. It's not just in laboratories that we need to worry about safety. In your homes, how many people have helped mom and dad cook in the kitchen? Okay, what do you use when you, okay, who puts stuff in and out of the oven? You or mom and dad for now? Mom and dad, most likely, until you get older and you get more comfortable doing it. When you do take stuff out of the oven, what do you wear? You wear oven mitts. So in a laboratory, in your kitchen, oven mitts are a piece of safety equipment that keep your hands from getting burned. You might wear an apron if you happen to help mom and dad in the garden, or if you have a hot tub or pool. There's chemicals that are used there, and you have to have the appropriate safety equipment to handle those chemicals safely. Now, we're in Edmonton. If you can convince your parents to do this. Go downtown to some of the underground parkades, the parking garages, and you'll see a sign. And that sign on to the underground parkades will say, no blank in the underground parking area. Now, Mom, Dad, what's in that blank? Fill it in for us. No propane. No propane in the underground parking area. The reason why there's no propane in the underground parking area is because, now imagine you have a leak in a gas tank. And gasoline is a liquid. If there's a leak in a gas tank, you get this puddle of gasoline. And you can say, hey, that puddle's underneath a given vehicle. That vehicle must have a leak. Propane is a gas. And if there's a leak, it goes everywhere. But propane is also heavier than air, so it settles. So in the underground parking areas, you end up potentially filling that underground parking area with gas. Now, if I remember this room correctly, that should do that. So we have a container right here. This container is going to simulate our underground parking area, and you're still allowed to smoke. Let's see what would happen, okay, if you walked into an environment that was filled with a propane air mixture. Okay, we'll go with that. So there we've got what was just, a few seconds, or not even a second, of fairly emphatic whoosh. Now, if you want to put your hand on top of this, you'll feel that it's quite warm. I'm only going to do the first few rows. You can do it too. Whoa. Now nice and warm, yeah. Something to cuddle up to when it's nice and cold outside. Now, what I need you to do is use your imagination. You saw this at the front of the room, and it probably was a little bit scary to people. Imagine if you were inside of this container. Okay? You had actually been breathing this stuff in. So it's in your lungs, it's in your nose, it's in your mouth, and it's burning. Causes significant damage to your lungs, okay, into your nasal passages. It does kill people. Imagine it was burning in your hair, or the hair that you used to have, because afterwards all your hair would be gone, and you'd look like me. Not that I had this happen to me lately, but, it's just the way it works. Talk to my parents about that. That's genetics, though, and we'll talk about that later. Okay. So safety is an important aspect. That is why that sign is there. What I'm going to do now, again, using the appropriate safety equipment, I've got a very small dish up here. Oops. There we go. So what you're seeing is what is projected right here. The reason why it's on such a small scale is because the chemical we're going to be working with is very, very reactive. It will actually react with the water. It's reactive with water specifically, and it will react with the water in your skin, the water in the air, everywhere. Okay? So, what I'm going to do is I'm going to prepare this dish. This is just a tiny amount of water. Putting a little water in there. And I'm going to make it such that we can see if there's a reaction occurring by adding some of that. That doesn't do anything right now, but it will in a little bit. If a reaction occurs, it will show it. There we go. And that should be pretty good. So that's preparing that. Basically, it's just a water solution. The chemical we're going to be working with is sodium metal. Now, sodium metal looks like any other metal you've seen unpainted. It looks exactly like aluminum. I'm going to bring a piece of it out right now and we can see it. Okay, doesn't look like sodium right now, or like a metal right now, but we'll see it in a second. Okay, so this is sodium metal. It's got a white texture or white coating on the outside. That white coating is its reaction with oxygen and water. That later. But an interesting thing about sodium is that it is really, really soft. If you ever go home and you grab a knife and you take some butter, that's exactly what it's like here. I'm just going to put the edge of my spatula into it, and I'm going to cut it like that. And so there we have got this, oops, wrong way, like that. Now, the inside edge is a little shinier and looks a lot more like a metal. It's actually oxidizing already. It's actually going white from the oxygen in the air. So I'm going to take a small piece of that, and I'm going to break this into a couple of sections. There we go. And now I'm going to bring back my original solution. Okay. So now let's see the reactivity of sodium metal in water. So there's a piece of sodium. Let's see what it does. You'll notice that it's turning the solution a pinkish color. That is the reaction with water. It's causing it to go basic. And I just want to get rid of the pink solution, so I'm just going to add a little bit more of that. Okay. Now the other interesting thing about sodium is, and I want you to just observe it for this time around, notice the shape of this piece of sodium. It is a long, thin, rectangular piece of sodium. When I drop it in here, it's going to pretty much instantly turn into a ball that rolls on top of the liquid. It is so hot, so much energy is being released, that it's actually melting the sodium at about 400 degrees Celsius. So here it goes, and it's a ball. It's a ball of molten sodium floating, reacting on top of the water. I'm very glad that it's forming a triangle, because sometimes it forms a pentagon and people get kind of scared. It does, honestly. I'm just like, sorry, that's my other career. It's okay, your parents will explain it later. Now what I'm going to do is we're going to look at the difference in reactivity of sodium metal. So I'm going to add a little bit of the oil that it was in. There it goes. And I'm going to add the last piece. There's the last piece. Oh, there it goes. It was reacting, and now it's not. It's now somewhat safe inside that ball of, this happens to be mineral oil, vegetable oil. But water gets in there as well, and water diffuses into the oil, and as it diffuses in, causes it to react, and the sodium gets kicked out and reacts wherever it wants. Get off the edge. You know, I got 2 balls of sodium reacting on the edge. Okay, fine. They can do that. So that just looked at some of the reactivity of metals. You might think of metals as being non-reactive, okay? A lot of stuff is made from metal. So, for example, just going to one other thing about safety, by the way, is, not touching equipment with gloves on. If I go over here, we've got a tank of gas in the far corner right here. It's made of a steel tank. But that reaction of that tank rusting is actually taking hundreds of years. If I were to leave that outside, it would still be there in 100 years, but it would be significantly rustier than it is. Whoa, how'd that work? Whoops. This is my instructional class, so I'll get rid of that later. That would be the webcam I wanted to go to. There we go. Let's ignore that. McDonald's. That's what I'm teaching right now. This tank over here is iron, and it will slowly rust over 100 years. This ball right here is also iron. Okay? If you were to go with your mom or dad into a hardware store, and you're doing some very, very fine finishing where you need to do sanding, you would use steel wool. to do the sanding. Steel wool is just finely divided iron. Now, if you talk to your parents about cleaning and they use those SOS scrubbers, you'll know that you will use them once and a couple of days later, they're actually pretty rusty. I'm going to put that down there. That's actually not bad. An interesting thing about steel wool, though, I'm just going to, well, lighting is an issue in this room. I'm going to do this. I can actually light it. And steel wool will actually burn. It's burning. Less. Now, I can speed up the reaction of steel wool burning by increasing the oxygen supply to the steel wool. You can see that it's burning right there now. And now I'm just going to add a little bit of oxygen. All right. Oh, well. There we go. So I've managed to use it all up. And if you look at this, yeah, it's visible on the camera, those glowing balls are actually molten iron. Again, so much heat was released with a little bit of that steel wool burning that it actually caused some of the other steel wool to melt and become molten iron on the table. We can, after this presentation, you can come up here and you can look at this, and you can see little balls of molten iron in the bottom down there. Go to this in a bit. I want to go from hot to cold just to spice things up a little bit. Now, upstairs, they are doing demonstrations with liquid nitrogen. How many people have seen the liquid nitrogen demo? It's pretty cool. Yeah, whatever. Did anyone tell you the temperature of liquid nitrogen? How cold is it? No, that's absolute zero. But you're close. Yeah, the orange? Minus 196, minus 197 Kelvin. Yeah, 196 is the number I have. So basically, for just a number to remember, minus 200 degrees Celsius. At minus, the coldest it ever gets outside is about minus 40, 45. This, taking the air and cooling it, all the way down to minus 200 will cause the air around you to condense into a liquid. And so if you haven't yet seen it, go up there and you can get really close with liquid nitrogen. I'm just going to show one interesting aspect of it. I'm just going to pour a tiny bit in the bottom. So I've basically got the divot of my pop bottle filled with liquid nitrogen. And we're going to see how much it expands when it becomes a gas. So I'm just adding heat to help the process along. And you can see that it expands close to, well, over 700 times its volume. There's still liquid in the bottom down there. And I've completely filled the balloon. And just watch, there's a lot more liquid still left in there. So as you're traveling down the road, your mom or dad might point out to you vehicles that are transporting cryogenic liquids. Natural gas is transported as a liquid. Oxygen and nitrogen are transported as a liquid. Why? Because you can put a lot more of the liquid in the same container and transport it to where it needs to go. Yes, it's colder, it takes a little bit of energy to do it, but you can actually ship a lot more in one truck as it travels down the road. No, between 7 and 8, depending on 7 and 800 times by volume. Yeah. So yeah, it's a significant. Let's put it this way: it's a lot safer to transport the liquid nitrogen, liquid oxygen, than it is to pressurize something to 700 atmospheres. Because if that ruptures, that's going to be a big explosion. So easier to transport as a cryogenic liquid than it is in a pressurized cylinder. This is a brand new demo for me and for us. We saw this on YouTube, and at the very end, and this was a science presenter in the United Kingdom, and at the very end of his demonstration, he basically said, and we believe that every home should have one of these. And everyone I talked to in the department said, yes, we want one of those. So now we have one. What is it? It is our own little rocket engine. Now, it's not going to take off and fly up, but what it's going to do is it's going to show you how a rocket system proceeds. Now, I'm going to show it such that it's half visible to the camera, half to the people in the audience, and I need to go over here and grab one of these splints that I saw. Rocket engines operate in space. Okay, they take things up into space. So they have their own supply of oxygen and fuel. An automobile takes air and uses the oxygen in the air. Rocket engines need oxygen at a much faster rate than that, and we're going to supply oxygen from the tank we have right behind us. Need to up the pressure just a tiny bit. Okay, so I also want to make sure it's not going to actually... Yeah, figured it would do that. Okay, not a problem. So we're working the bugs out of it. I had to steal the oxygen cylinder from someone else. Okay, so here's the supply of oxygen. The fuel is actually the cylinder right here. So the cylinder that's in there is acrylic. It's plastic. That is what we're going to use as our fuel. So it's actually going to burn away the wall of the cylinder. That's not as crazy as it sounds. If you've watched the shuttle launch, the two solid rocket boosters on the side is actually a solid, and is actually burning away the walls of the engine, of the rocket. Now, it's encased in metal, but quite literally the inside of it is completely solid, and that just burns outwards, and that's how those rocket engines work. So I'm going to light it, I'm going to go turn off the lights, and then we can see it operating in the dark. What I need is a source to start it. I'm going to put that in there. Whoop, that didn't work. Okay, that's going to kick that out pretty quick. So I can go like that. That's low on air. That's just on a standby mode. And if I just crank up the amount of available oxygen, you can see that we get a significant increase in the amount of what would be propulsion coming out of my engine. One more time. And we'll shut it down. Now do you understand why every home should have one of these? That's just cool, honestly. It's just cool. My students have not yet seen this. They'll actually be seeing it this upcoming week. So shh, don't tell anybody. You watch it through video anyway, so yeah. What time is it? Oh, I got 20 minutes. Yeah. How much thrust does that thing put out? Not a lot. Obviously not enough to move the block. But I honestly don't know. You saw it. It was actually fairly high energy coming out the end. It would be reasonable, okay? It would move small, lightweight objects. Yes. It would basically be able to move itself without a problem if it was on wheels. Actually, that's an idea. Let's put this thing on wheels and see it move down the road. Or at least on the table. Hey, that's the innovative idea. Wheels. Next step. Yes, sir. No, it's burning the acrylic. My acrylic rod slowly eats away from the inside outwards. So I have to actually watch the thickness of this. So eventually it's going to get too thin and I have to replace it and use another one. Yeah, so just like I was commenting about the solid rocket boosters, those things, they burn all toward the edge and then they're ejected, so you can actually refill them with rocket fuel and run them again. Question? Oh, how does it make the sound louder? That loud sound is actually energy being produced because I'm putting gas in here, and as it heats up and burns, it's pushing a lot more gas out the end. So that sound you're hearing is the gases escaping from the nozzle down at this end. If you had an automobile that didn't have a muffler on, you'd hear the same thing. You'd hear a loud, like loud noise because the gases are escaping out of the cylinder. Okay? Sit down. What? How hot does it get? Hot. I don't know. Okay. You come up here and let's see how long it takes for you to get third-degree burns. No. Okay. Now, let's look at these two pop bottles. And I'm kind of limited by the camera there. We've got two pop bottles here. At one point in time in the past, these two pop bottles were the same size. Okay? As a matter of fact, at one point in time, all the pop bottles of everything you've ever drank used to look like this. Okay? Basically like a little test tube. Now, how are pop bottles made? Every pop bottle starts off looking like something like this. It's put into a mold and it's heated up, heated up, heated up, heated up. Once it gets soft, air is blown in and it fills out the side of the mold, and voila, you get a pop bottle shaped like this. If it's a different mold, it's a different shape of pop bottle. But all the pop bottles basically start out looking like that. How do we go to this intermediate state? Well, it's okay. Like temperature. You're okay. It pops. No way. It's okay. How do we get to this intermediate state? You can do this at home under the supervision of parents. Now, if you take a regular pop bottle, fill it full of water, okay, hot water, loosely put a cap on there, just loosely, and then put this into a pot of boiling water. So basically the water is able to leak out the lid, but putting it into a pot of boiling water, after about an hour at 100 degrees Celsius, it will have shrunk back down to this size. Basically, this pop bottle is like taking an elastic band and stretching it and freezing it in position. As you cool it down, it's frozen in position. By putting heat back in, you get halfway to the original starting point of the preform right there. All right, so there's that. Now let's look at another aspect of these pop bottles. This is a model. Now, these molecules that we've got floating around over here, I'm missing a methyl group. Some people in the audience might know what that means. If anyone sees a little piece with 3 or 4 atoms on it, I'll love to have it back. These are models. How many people here play with Lego or Connects or something like that, right? You make things, and you'll use your imagination that these things are cars, buildings, people, whatever, dragons, boats. Well, as scientists, we do the exact same thing. We make models because it's really hard to see the individual molecules. And so this is a model of cocaine, actually. So we can see where it's flexible. We can see where it's fairly rigid. That's a model. Science is all about making models. This is going to be a model of an automobile engine. Okay? More specifically, the cylinder in a car engine. We have that. And we're going to take... Now, there's a test in this, so parents, people who know about cars, please pay attention. We're going to put a piston in one end. A piston is the thing that moves up and down and actually takes the combustion and turns it into the vehicle moving forward. Now, how many people have finished grade 9 science? Okay, how about grade 11 or 12 chemistry? Grade 11 chemistry, actually. You did? Really? Just last year, eh? Okay. All right. If you've done grade 11 chemistry, you'll be able to do this. You know what's in the air around you. The air around you has nitrogen, I heard it, oxygen, and does anyone ever know what the third major component of air is? I'm going to go with that. Go ahead. Yep. It is argon, yes. Nitrogen, oxygen, and argon. A lot of people think it's carbon dioxide, but it's not. It's nitrogen, oxygen, and argon. Okay, we can measure how much oxygen is in here. This is fuel. This is just camping fuel. We can calculate how much fuel we need to react with the available oxygen. And when we do that, that would be the fuel injection component of my automobile engine. Now, for those people who are familiar with how automobile engines work, what's the next step in an automobile engine cycle? Okay, I heard spark at the front, and I heard compression, yes. The one thing that my model can't do is it doesn't compress the cylinder. I can't take my piston and move it up so it's about a 10-to-1 compression. So what you're going to hear is the same amount of energy being released, but a little bit slower. The impulse is less. So this is the amount of energy released every time an automobile cylinder fires. That's okay. You weren't in any real danger. Is that your daughter? Okay. You have more than one? Oh, so you want to keep that one, right? Oh, okay. You can bring it down here. She's fine. She's fine. She's fine. She's fine. All right. That's why I aim high. Okay. Who would like to see that again? Okay. I'm going to put my piston back in here, and I'm going to need your help. Do you want me to put in less fuel, the same amount of fuel, or more fuel? Okay. Let me try that just with a show of hands because I didn't get it. Less fuel, the same amount of fuel, or less fuel? Oh, fine. You want more fuel. A little bit more or a lot more? All right, if I have to. Can I have Mom over here? Now, right there is fine. The key point of doing anything nefarious is to get rid of witnesses. So can we come over here? You did good in my class? I did. Yeah, but you posted something very negative about me to like rate my professor. I can tell who does those things. I never did rate my professor. Yeah, okay, sure. Okay, I expect something very positive after you do this. Now, I need you. She was my student at one point in time, so this is actually a little bit dangerous on my behalf. I'm just going to walk over here. Okay? And now, this is, your mom's going to get retribution for, me nearly trying to take you out, okay? You can go look up the word, retribution. You can point that at me. Center of mass. Okay, pretend you're a police officer, center of mass. That's the face. That's a little too low. A little higher. There we go. Good. Okay. Now, this is allowing her to get retribution for probably making you do homework and all this sort of fun. Yeah, okay. Anytime you want. 3, 2, 1, go. Try it again. I trust students a lot, just not super amounts. Thank you very much. Why didn't it go off? Too much fuel. Yes. 2 things. Not enough oxygen. Okay. All of the oxygen was used up in the first reaction. But second one is too much fuel. Now, if you have a lawnmower, you know that if you try to start it for a long period of time, it doesn't start. You flood the engine. You have too much fuel in the engine, and it doesn't actually go. Good old days, cars used to flood too, but now that's all been fixed. In science, if you're a student, you are working in labs and you do experiments, and sometimes you think in the back of your head, if I put in more of the chemical, things are going to go better. Well, sometimes actually more makes things not go at all, as you see here. So it's the correct quantity that needs to be put in order for things to proceed ideally. All right, I have just one final demo left, and that will take us till 3:20, which I think is the time that they said they wanted me done by. All right. I'm going to clean up just a tiny bit so that I don't have accidents in the lab. That's also an important factor, as you do in your kitchen as well. You want to keep the area clean so that you don't accidentally knock things over and the like. What's he doing? You don't want to know. Excellent. All right. So, oh well. What I have here are a couple of balloons filled with different gases. How many people have been in a hospital, seen someone on oxygen? They have signs up that say, caution, no combustible, no smoking, oxygen in use. Very true. It used to be that they were to tell you that oxygen is flammable or explosive. Not so much true. This balloon is going to sit right there. That balloon is filled with pure oxygen. And we're going to see what happens when we light pure oxygen, as long as the balloon stays there. You can turn the lights back on. Someone said, "Ow, that's my joke." Okay, not a lot. It's like a balloon just popped. There was nothing obvious that said, hey, big flames are happening here. But we know, the other one, this one, that you need a fuel in order to have flame. And so one fuel that might be making a comeback in terms of renewable energy is hydrogen. So this balloon is filled with hydrogen, not helium. Okay, we'll do that. We'll angle our camera up, 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 up. Okay, we'll bring the balloon down a bit. There we go. All right, so that balloon is filled with pure hydrogen. I want you to compare this one and the next one. So if I could have the lights down, please. Oh, safety first. There we go, pure hydrogen. Lights, yeah, thanks. And lastly, we can mix. Lastly, if we actually mix together the fuel and oxygen, so a hydrogen-oxygen mixture, so this is a hydrogen-oxygen mixture, and you can watch this as well. Now, in terms of safety equipment for this, you can turn the lights back on for just a second. Appropriate safety equipment is this. Now we have got, okay, in the previous one, we saw a lot of flame. That is because in order for hydrogen and oxygen to react, it has to be in contact. There was no oxygen inside of that balloon. It had to go outwards to get to the oxygen. Here we've mixed the two together. So the reaction should be a little bit faster. And so this would be as close as you're going to get to an explosion. So if I could have the lights off, and everyone in the room, please cover your ears. Everyone, time to cover your ears. 3, 2, 1. All right. Thank you very much for your time and attention. If you want to come up in here and look at these metal balls, that's great. And please enjoy Science Fun Day. Have a good day.